So in this final recording, I'm just going to take you through troubleshooting a couple common problems when it comes to fitting data. So I'm going to try and zoom through these as fast as I can so I can make my point as quick as possible. So first things first, let's look at this first example. We're going to plot it like we usually do. Once again, it's quite similar to the first one. And if we do, we can see, once again, we gain something that looks like a surge plot, which is great. But notice that we don't start and we don't end at 0. Okay, so clearly the graph has been shifted up from the regular surge graph. Okay, so a regular surge graph won't be able to accurately model this. So what this means is that we're going to need to rewrite our surge model as f of x plus some constant, and then it's going to be our regular surge model, which is a x e to the minus bt. Okay, so we can do this in two ways. We can either sort of guess what our constant is at the start and plus it onto our model. So we type something like, if we wanted to guess what our intercept would be shifted by, we can guess 30 plus what our model usually would be. Or we can incorporate this c as a factor and get Excel to deal with it for us. So what I'm going to do in this example is just get Excel to do what the best guess for this would be. Okay, so I'm going to set three values, A, B, and C, and arbitrarily set them to 1. Okay, now I'm going to copy the model that I copied down here, and that's going to be C plus A times X times E to the minus BT. Okay, and now I'm going to lock all the cells we need to lock. So this one here, this one here, and this one here. Okay, and we're going to drag this down and just get a bunch of 1s, which is fine for now. So once again, we're going to define our error as the difference between the model and the profit, our predicted value and our experimental value. And then we're going to find our error squared, like so. And then finally, we'll do our regular mean square error. Okay, and we're going to call this the average of all of these values, as always. And we're going to go over to solver and minimize this error by changing these three parameters here. Okay, so let's do that now. And we've got a solution, which is good. And if we go ahead and plot this solution, model, oops, what's going on? I've selected the wrong one. Okay, it appears there's been some sort of error, so let me just double check what's going on here. Apologies, I've locked the wrong thing. So bear with me. I want to lock this one here. Thought it looked a bit weird. So if we try that again, apologies for that one, and we'll rerun the solver. So all our constraints that we entered are saved. We'll get some real values, okay? And you can see solver's manually adjusted what our shift of C is going to be to the most optimal value, as well as our A and B values. And like I said before, you didn't need to get solver to do that for you. You could have just entered that as a direct value in here. So you could have said 30 or whatever and then ran solver as usual. But that's the first problem and sort of how to go about fixing that. And the second problem that we're going to look at, I've already got some stuff set up, is a model of another surge. And you'll notice that with our data, we've got a really high density of points towards the tail end of the graph and very low density points at the start. And you might think this is not a problem. And especially when you're using digital technology to try and take your graphs, often there'll be a really, really long taper off. So you might have, say, 6 points in this peak region, and post peak you have 600 points. So the effect will be more pronounced, as you'll see, but this is like a small scale kind of example. So once again, if this is a surge, our model is going to be A times by X times E to the minus BT. Oops, it's meant to be minus BT. Okay, and we're going to lock everything we need to lock. Lock that one and lock this one. Okay, and we're going to drag down like so. Cool. And we can see this is obviously not great, so we're going to run through our error process. Oops. Yep. Drag that down. Error squared. And just to mind you, I label these things because it's good to be organized in Excel, but it doesn't actually do anything to the numbers by having these labels here. And then NSE is the average of all of these numbers here. Excellent. Okay, so we've got this, and we can run solver by selecting this as our parameter to minimize, and we're going to be changing these two. Okay, and we'll see that if we run this, you get a graph that's okay, but it's not probably the most accurate fit. And you think, well, how come Excel is doing that? And essentially what's happening is Excel is really trying to copy this part of the graph because there's so many points there, and hence it's contributing to a lot of the mean square error. So by trying to minimize the area on this side of the graph, it's ignoring the area at the tail end of the graph where there's very few points. So you can see that compared to what our real peak is, our model peak is really low. So how can we go about fixing this? Well, it does vary depending on the problem. However, there is a bit of a solution to doing this. And essentially what we want to do is, instead of taking all of our points to sample, what we're going to do is we're going to take the average of some sample points. Okay, so once again, we're probably going to take individual points like this. So if you click on a cell and add a comma, you can add individual points. So what we're going to do is we're going to try and make it as even as possible. So we're going to take 3 sample points at the start. Perhaps we'll take these 4. And then we're going to try 4 sample points on the tail end of the graph, and we'll try and space it out as best we can. Something like this. Okay, and what this is going to do is not concentrate our MSE so much in this area of the graph, but try and distribute it evenly across the whole thing to hopefully get a nicer fitting graph. Okay, so don't worry if that doesn't make too much sense. The point is that we're just trying to fit the best possible graph here. So if we go ahead and rerun solver, it's got all our stuff saved already. Hopefully we can see in this example that we get a better fit, and we definitely do. At the very least, our maximums line up much better with our y coordinates, and overall it does look a whole lot better. So the idea is that you just want to fiddle around with some different sets and try and equally distribute different key sections of your graphs by picking out particular points. So essentially you're just sampling an even distribution of points along your graph, and hopefully that will improve your modeling process. So I hope these videos have helped, and yes, thank you for listening.